much, Alex, for the introduction and for the invitation to this workshop. It's really been a great week so far. So today, and as we briefly mentioned yesterday, we will discuss a new application in coding which deals with a broad range of non-volatile memories. And here is a collection of new applications that are definitely primed for innovations in coding theory. Okay, as we mentioned yesterday, non-volatile memories, just think of them as flash for the moment, offer fast access and require less power consumption than hard disk drives. And they are quite ubiquitous, ranging from digital personal electronics to cloud storage in the form of SSD drives. Flash memories are based, as a prime exemplar of non-volatile memories, are based on a large array of floating gate transistors. Information is stored by capturing the electrons on the floating gate of these transistors, and that is how we store the information. However, even though this technology is extremely promising and it's bound to replace hard disk drives in many applications, and it already has indeed replaced hard disk drives, there are certain challenges or shortcomings that need to be overcome. So in particular, wear out and reduced device lifetime have now become a central issue. So the endurance in terms of the device actually decays very fast. It decays exponentially fast, and while we are increasing the density of the device only 2 or 3-fold. So this is an extremely unfavorable trade-off, and it's due to a number of different reasons. And they have to do with the way we access these devices. So I'm just going to highlight some of the major reasons for this, and then we'll see how some new coding techniques can help overcome these physical limitations. So RAD asymmetry. In a nutshell, increasing a cell level is easy. So let's say 0 is a lower level and 1 is a higher level. If you want to go from 0 to 1, that means you're injecting charge. For the moment, let's assume that's easy. Decreasing a cell level, meaning removing a charge, is hard. The reason for this, and this has to do with the way these cells are organized, is due to the physical architecture of these cells, is that you have to access the entire block and erase an entire block. That means you have to access and erase millions of cells, even though, in principle, you may want to only erase one. So you are maybe in a situation when you're erasing and updating cells that in reality should not be updated. Intercell interference, Paul already talked a little bit about this yesterday, so we've seen a new coding approach to this. Intercell interference means that programming a cell may impact adjacent cells. You may inadvertently raise the level of an adjacent so-called victim cell. Charge leakage. Cell levels decrease over time. So these are not perfectly chiseled machines. They actually wear out. And so they leak charge. So what you store is not necessarily going to equal to what you read later on. And so this whole compounded effect amounts to what is known as a finite lifetime. So this is one of the peculiarities of these devices. A device can only be programmed finitely many times before it is deemed unreliable. And so our goal here is then to extend this lifetime and to keep it at a target reliability for as long as possible, because nobody wants to be buying really fast SSD drives for your laptops that work really great for 3 months and then crash. Just to give you a sort of a sense of how severe these numbers are, TLC device is a sort of state-of-the-art device. It refers to a technology that stores 3 bits per cell. We'll talk more about that technology in the context of some coding solutions during the talk. Without doing anything special to it, without doing any coding, you can wear out the device in a matter of months, which is really, really, really pessimistic. Okay, so now you see there is a broad range of problems that we are encountering. And of course, coding-based solutions have been with data storage from day one, and they have actually been used very successfully in a range of data storage systems. However, due to these strong asymmetries that span both time and space, now, there are a lot of opportunities to innovate in coding beyond the Hamming metric. In fact, we will appeal to some existing old results in coding theory that have found a new home in the context of NVMs, and also develop some new techniques at the same time. Okay, so Today, I will share with you some of the recent results of ours in the context that are coding-inspired approaches to improving or addressing the flash unreliability. So we'll talk a bit about so-called graded bit error correcting codes for variability within the cell. We'll talk about some new results on WOM coding to defer costly races. We'll talk about constraint rank modulation to mitigate intercell interference. A new type of data thresholding called the dynamic thresholding that attempts to do error balancing. And I will very briefly describe a class of graph-based codes, notably non-binary LDPC codes that are optimized for flash. Okay, in the end of the talk, and I think this is probably of most interest, I will also discuss a range of other problems that are both coding and not just coding based that can be studied in the context of improving reliability of these memory devices. Okay, so let's get started. As we already established, flash memories possess strong asymmetry. So what I'm showing here is, and this was collected from on a real TLC device. Again, TLC is a device that stores 3 bits per cell. That's just the naming we use. So here what we show is that we did a careful data collection, and we noticed that most of the time, out of 3 bits in error, out of 3 bits in cell, only 1 bit was in error. Frequently, much less frequent was 2 bits were in error, and even less frequently were 3 bits in error. Okay, so let's see how we can exploit that. So then the goal is to actually construct a coding scheme that works rather than ignores these properties of the error patterns that we have encountered. Let's do an example. So suppose this sequence is stored. The way I'm grouping the information here is in triplets. So each triplet corresponds to 1 cell, since we are storing 3 bits per cell. Now I'm just unfolding them in a long sequence of zeros and ones. So you can think of this, how many we have, 1, 2, 3, 4, 5, 6 cells, each storing 3 bits. Because of the errors that have happened for a variety of reasons that we mentioned before, what we see is not what we stored originally. In fact, I'm marking them in color where the differences are. There are many different ways in which you can characterize these types of errors. You can say, well, okay, let me just look at them at a symbol level in groups of 3. You can say, well, there were 3 symbols that were in error. Namely, I'm just looking at the collection of triplets that have experienced some errors, right? There's 3 of them. Now, I can be a little bit more refined and say, well, not only there were 3 symbols in error, but whenever the error occurred, at most the number of errors that I see is 2. Okay, just based on this example that we see. I can be even more refined than that and say, well, there were 3 symbols in error. There were at most 2 erroneous bits per erroneous symbol, and it occurred exactly here. And there was only 1 symbol that had 1 bit in error. So the sentence is a little bit convoluted at the moment, but the idea is that what we want to capture here is the fact that most of the time there was a very few number of bits in error per erroneous symbol. However, we do want to account for the fact that there may be some errors that have more than 1 bit in error. So what are the kind of codes that we would build for this? If you're looking only at the symbol level, you say, okay, let me then just go and pick up a standard symmetric error T-symbol error correcting code. In this case, perhaps we can look at code that corrects T symbols. I have not introduced the code, but this is how we would do it. T symbols, which has at most L bits in error. And sort of based on this sentence under item 3, I can define a code that has more parameters associated with it. In fact, it has 4 parameters. Parameters T1 and T2 will collectively guide me in number of erroneous symbols that I seek to correct, and L1 and L2 will tell me how many erroneous bits per erroneous symbols I want to correct. The reason why this sentence is exactly like this is actually for mathematical reasons when we built our codes. Okay, so here is one way of constructing these codes. The construction is based on tensor product operations. So the idea here is that we are actually utilizing as underlying codes our existing symmetric error correcting codes, but we are combining them in a careful way so as to be able to correct the error patterns of the type that exactly we see in practice. If we were to just blindly apply symmetric error correcting codes, we are doing more than we should, because then we are accounting for the error correcting capability for the type of errors that may not exist. Okay, so we start with the binary code H, just a regular binary code H that has error correction capability L2, which has a parity check matrix H rather, whose submatrix corresponds to a code that has error correction capability L1. Then we introduce two additional non-binary codes, symmetric non-binary codes. They're defined over appropriately chosen fields so that these operations work out and we can apply tensor product operations. They are both, again, symmetric error correcting. One has error correction capability T1 plus T2. The other one has the correction capability T2. When you put everything together, indeed, we get a parity check matrix of a code that exactly corrects the type of errors that we're interested in, namely those that have a total number of erroneous symbols governed by T1 plus T2, of which at most T2 will have no more than L2 errors, erroneous bits. I should point out that this was inspired by early work by Jack Wolf from 1960s, when he proposed a scheme that only has one tensor product operation. Clearly, this was not in the context of Flash. This was in the context of correcting bursts of errors. So we have been able to sort of go back in the past and dig up some old results that can serve as a starting point and then build upon them to provide a family of codes that are actually fit the needs of what we are looking for in Flash. Slight extension. Not only there is a variability amongst the errors within a cell, some cells are just naturally better or worse than others. In fact, we also observed, and some other people have observed, that some cells are just naturally more unreliable. Not many of them. There are just some that are more error prone. These are sort of orders of magnitude statements. Please don't interpret them as exact numbers. There's a very small fraction of errors that accounted for, small fraction of cells that have accounted for a non-trivial amount of errors. And with a slight modification of our scheme, wherein we only offer limited programming, or rather allow limited programming into those few select highly unreliable cells, we can do a little bit better in terms of our construction. So here's one plot. The x-axis is program and erase cycle. This is your lifetime. Y-axis is a page error rate. You want that to be as low as possible for as long as possible. These curves all get worse over time. Remember, we have that issue of wear out, so things get worse over time. The curve on the red curve is your non-binary BCH code. This is pretty much what people would do in practice, or even a combination of some other codes like binary BCH code, or a combination of 3 parallel binary BCH codes. These 3 curves are all symmetric error correcting codes. Mind you, for us, the errors are not all created equal, and if you just apply symmetric error correction, you are essentially allowing your code to do more for you than it does. And where do you pay the penalty? In redundancy. So with a slight, so our schemes, the original is in pink, and the one that is modified that only allows for limited programming into these select few cells, we can essentially push this to the right. The reason why these curves start here is because we did not observe any errors until late into the lifetime. Yes.
Can you know in advance which cells don't work?
Yeah, so there are many different ways in which you can do that. For example, a cell that has, there are different mechanisms to do that. Here is one way to do it. The cells that have repeatedly give you erroneous outputs on some prescribed number of most recent writes. For us, actually, it was sufficient to only identify 2 such cells in our example. So 2 out of million is not, it was not really a big deal to find.
Is this graph? This is
on a real cell? No. This is on a real device. This is on a real device. So the entire coding machinery is developed independent of the device, but in the sort of spirit of this workshop, we went from practice, which is data collection, this motivated the development of new coding scheme, and then we tested this back on this. So what I'm showing here is for a TLC flash device, which is the one that stores 3 bits per cell, but number 3 is completely, is a parameter that we can tune. It is not native to ours.
How is that easy to actually do?
Yeah, we have. So this was part of this work was done in collaboration under an NSF project with the colleagues from UC San Diego, who were kind enough to share some of these access to flash devices that we were able to test this on. So you actually probe the cells and see, see what you get. And so that's essentially how you have to do it. All right. Another sort of coding-inspired approach, again, a little bit of flashback. Write once memories is something that was developed actually a long time ago by Rivest and Shamir 30 years ago, and then other people have worked on this problem. And here is how it goes. Here, think of it for people for whom this will be, for some of you, this will be a good analogy. For a younger audience, probably not. Think of a punch card. Okay, so think of a punch card. You punch the card. Once you punch it, you can't unpunch it. But even when you punch it, the unpunched positions, you can still keep punching, and that's how you can store more data. So what this means, if you think of it as a cell, cells are irreversibly programmed from 0 to 1. And that means that if we invoke some kind of coding mechanism, we can write additional information on top of previously stored information if we can combine some new coding techniques. The reason why this is interesting now is that you can write information on top of previously stored information without invoking this expensive erase. And remember, for us, erase is a very expensive operation. And in fact, these connections for Flash were recognized by Andrew Jiang and Brook and Jacobi and Siegel and so forth. I will introduce one of our recent schemes. First, let me walk you through how a code like this would work, okay? So this original code is due to Rivest and Shamir from 1982. So here is how it works. You have an information, which only in our case, it's a very simple code. You take 2 bits, you encode it into 3 bits. Here is an example. Everything is done according to this table. Let's say you want to do this for 2 writes. So we always look at a prescribed number of writes because things become progressively more difficult as the number of writes increase. And it's hard to maintain this constraint that we don't want to go back from 1 to 0. In any case, let's do an example. In write 1, you start with 0, 1, and according to our table, you encode 0, 0, 1. On write 2, you go to the table. You want to encode, let's say, this message, 1, 0. So you would store 1, 0, 1. So notice that, at least in this example, 1, 0, 1 became 1, 0, 1. So we really never had a case that 1 transitioned back to 0. So you can write 1, 0, 1 on top of 0, 0, 1. And in fact, this was actually a very carefully constructed table, and you can check that indeed all these transitions are possible. If you were to write the same information twice, you wouldn't go from 1, 0, like for example, you want to write 1, 1 twice. You wouldn't go from 1, 0, 1 to 0, 1, 1, because it would be illegal. You just stay at whatever you had encoded already. In any case, all these possible combinations of writing 2 bits twice work. And that is essentially the Rivest and Shamir original code. Okay, so we need a few definitions. We are looking to construct a code that satisfies a so-called WOM constraint. In the sense, it's a very natural constraint now that we have seen an example. J is our generation, or number of writes that we're going to execute this. Rivest and Shamir code was over a binary alphabet. We're also interested in extending this to non-binary alphabets, given the interest in very dense non-volatile memories nowadays. So we are looking to build codes such that on every subsequent generation, what you write always sits on top of what you have previously written, irrespective of what you have previously written. Sum rate is a quantity that we're interested in, so we want to be able to store as many code words as possible. So we are looking for codes of having high sum rates. If mj is the number of code words you can store at generation j, then the rate at that generation is log mj over n if you're encoding over n cells. And the sum rate is simply the sum of all possible rates. Capacity, of course, is the best you can do. Capacity in the example that we have seen is 158, and that code itself gave you 133. Okay, so recent work on this topic has given this sort of applicability to this type of codes, to non-volatile memories. There's been a lot of very nice recent work in the context of binary WOM. What I will show to you today is one of our recent results on non-binary. Okay, so how can we, yes, please.
Capacity here?
So there is the combinatorial formula for this, yes, that is basically it shows. That was also due to Rivest and Shamir. Yes, these are results back from the 1980s. Yes. It is log n plus t minus 1 choose log of combinatorial term, the very simple combinatorial term, so it's easy to plug in for the sum rate. Okay. All right, so now we have some intuition of how to build a binary binary WOM code. And like I said, thank you. And like I said, these results have been since most recently very significantly extended, but now you've seen an example how this works. Okay, let me show you an example of a non-binary to write WOM code. Here, in order to make the construction work, we require the number of levels to be a number that is divisible by 3. So the total number of levels is such that the total number of levels is q, and q plus 1 is divisible by 3. So now I'm going to divide these levels into groups of L. So the first subset are levels 0 through L minus 1. The second subset is L minus 1 to 2L minus 1. So notice that L minus 1 is common. So these are not partitions, they have slight overlap. And then third subset is from 2L minus 1 to 3L minus 1 for the total. Okay, here is the way we can encode. So suppose we have available a binary to write WOM code, and I just show you an example of that one. That was your Rivest and Shamir code. On the first write, we're going to pick some arbitrary message of length n over ZL. So it's arbitrary message of length n. We're going to pick a first generation code word from our constituent binary WOM code. We saw an example of the one of length input size 2, length 3. And depending on what the entries in that code word are, in entries in the code word U are, we are going to write either in the position mi, or you're going to write in that position either value mi or mi plus L, where mi is the mth entry in your message. So what that means on the first write, you're restricted to only write to these first and second subsets, right? So you're only writing to lower levels. The intuition being is that you don't want to write up too high, because then it's going to eat up away for what you can do later, okay? On the second write, you pick a different message, again, arbitrary message. You pick a second generation code word from your underlying code. And now again, you either write in the value either that SI is the ith entry in your new message S. You either write value SI plus L minus 1 or Li plus 2L minus 1. And so what that means here, you're only writing on the second and the third subset, okay? So if you do this carefully, as we have done here, you're guaranteed that you're only going up. You're sort of avoiding these illegal transitions. And here is just an example. We've seen this table before. Let me just walk you through these numbers. So let's say your information is 0, 1, that you want, thank you, I'll probably just skip some other examples, okay? 0, 1. According to our Rivest and Shamir code, we map that to 0, 0, 1. Your input message is 0, 1, 2. Here is 0, 1, 2 again. So essentially this Rivest and Shamir code word modulates these values. So 0 stays at 0, 1 stays at 1, but 2 now becomes 5. And likewise here, 1, 1, 1 modulates 2, 1, 2, so it becomes 7, 6, 7. As you can see, this message strictly sits on top of this message. Okay, all right, so this very simple construction that I've just shown you offers the codes of sum rate of 4.5. The capacity is, again, according to the same calculations, is 517. These are very short codes. Your question is, can you do better? In fact, you can. And we have developed a new code family that is just a little bit more combinatorial involved, but it sort of carries over a similar type of intuition that we've seen in this example. Here we just, instead of using one constituent code, we're using 3 constituent codes. And one code is quaternary code with the low numbers of 2s and 3s. And whatever was not encoded in that code, we use that leftover information to encode using 2 constituent binary WOM-codes. And these are the new sum rates that we have been able to achieve, and this is the capacity, and as far as we know, this is the best you can do. This also extends to this case where you restrict yourself to have the same number of writes, the same number of code words on each write. Okay, here's another way of looking at things. Rank modulation is a new data representation. It was pioneered by Andrew G. Yang. And here, the key idea is that instead of representing values in the absolute terms, which correspond to threshold voltages, y-axis is threshold voltages, you represent information in terms of their relative ranking. Okay, so if these are the threshold voltage is essentially how much it corresponds to the information stored in a cell, essentially how much voltage do you need to turn on the cell. Okay, so suppose these are the absolute values for the voltages, 2.8, 1.5, 2.6, and so forth, okay? So instead of looking at these numbers in the absolute terms, let's just look at their ranking. So this would be first one, second one, third, fourth, and fifth. So this now induces a permutation over integers from the set 1 through 5 of 1, 3, 2, 4, and 5, right? What are some advantages of this scheme? Remember, wear out was one of the problems we want to deal with. Just imagine if everything drops down together uniformly, then the relative ordering is preserved. So this is one of the advantages of this scheme. However, intercell coupling is a problem still in rank modulation, in the sense that inadvertent charges can change cell rankings. And here is an example to illustrate why this is so. Suppose we start with this setup, where our original permutation is 1, 2 through 10, because this one is the highest and this one is the lowest, and they all go down. Now suppose this is the permutation we start with in our rank modulation. Now suppose we want to represent a new permutation, okay? So how we do that? You want to represent a new permutation, we need to inject just enough charge in corresponding entries to push them enough to change the relative ordering. So this one must be the highest, and this one must be now the second highest. But see, like I'm adding a lot of charge in these 2 cells. And intercell interference occurs when 2 cells are strongly programmed, if you will, and then something happens in the middle. Okay? All right, so as we say here, now we inadvertently raised the level of cell. Okay, all right, I'll just speed up. Okay, block. We can essentially what we come to is that we get the permutation that we didn't want, right? So then the idea is that now we have, even though there was only one cell that was increased incorrectly, we have induced some positions in permutation that are now in error. So the idea now is to constrain the difference between adjacent cells, adjacent cell ranks, and for that we introduce the notion of a single neighbor K constraint. And so basic idea is to now study permutations that are constrained. So not all permutations, but certain constrained permutations. For example, this permutation meets a 2 constraint because there is no gap more than 2, but it does not meet 1 constraint because 1 and 2, for example, differ by 2. Okay, as one of our results, we have actually did a count of all possible permutations, constrained permutations under the constraint that we have introduced. We have a lower bound and upper bound, and it uses some combinatorial arguments to do that. We also computed the capacity of such codes, both for the polynomial case in terms of the constraints and for the constant case. And we have also introduced I'll just skip some details. We have also introduced new codes that follow in the class of constraint permutations and offer error correction capability. We have capacity results and also asymptotically optimal codes for that. I'm going to skip this topic because I'm out of time, and I'll just show you one more plot. Okay, so we also developed a class of non-binary LDPC codes that are optimized for a varying number of reads. These are codes that provide so-called soft information, which is what people in practice are very much interested in. Here what I'm showing on the x-axis is the row bit error rate against the frame error rate. Being to the right means it's a stronger code because you can tolerate more errors. BCH code is the one in black, and our codes are the ones in blue. So they offer superior performance both relative to binary LDPC codes and unoptimized non-binary LDPC codes, and optimization has to do with how we design a code so as to overcome these error patterns that we see in Flash. Here are some publications of ours on this topic, basically covers the material I said today. There is many other interesting topics. This hopefully will be of interest to the audience here. Investigations are primarily focused on the algebraic constructions and very briefly on graph-based results. But other modern codes, polar spatially coupled, lattice codes, there's a lot of interest in all these for NVMs to deal with all kinds of errors, both permanent and transient errors. How to deal with coding that is attuned to changing noise characteristics of the channel. We have asymptotic optimality in terms of certain code constructions. Can you do better? Can you have better bounds? What are the complexity and performance trade-offs? We are typically interested in worst-case performance. However, average-case performance may also be of value. NVMs, I talked primarily about flash memories. There are other types of non-volatile memories, including PCM, phase-change memories, SAT RAM, that also share some of these operational asymmetries with flash, and in addition have some other additional properties. And they're all really primed for new coding-inspired approaches that go beyond the Hamming metric. It doesn't have to be coding for the people who are working on other topics. Parameter estimation, so new signal processing techniques for characterizing the channel. We used in one of our experiments, and when the question came up, we used actual data, but it would be nice to have a closed form solution for these channels. There is some very recent work on this topic. People currently use Gaussian because that's just a good starting point, but we all actually already know that this is not a good model. Communication methods for Flash, how to do detectors for intercell interference, equalization, and so forth. A lot of room left to do capacity calculations. These channels, when you have fixed number of reads, become quantized. Non-asymptotic performance analysis, applications of probabilistic methods, and a little bit more speculative, but perhaps even the usage of interference alignment type of techniques to address the issues of interference in these channels. That concludes my talk. Thank you very much.
Maybe one quick question while Emre is setting up. Is the question by?
No.
Okay. So why don't you set up? We are. Oh, you're all set up.
Yeah.
Okay. So then, any question? Quick question?
Yes.
So, when you're reading a cell, you have an A to D, right? So if you're going for 3 bits or something, what's the trade-off to going to more bits and then working with soft?
Yeah. So that's a few reads is much better because there is one of the things we want to deal with is read latency. Fewer bits is better. However, you have a much better reliability about the content of the cell if you have multiple reads rather. So typically, for example, I'm quoting Samsung from what they've told me. They don't want to go above 7, but they would prefer to keep it at 1 for as long as possible.
And these reads are all 1-bit reads, right?
Yes. So exactly the way it works, you're going to set up multiple thresholds. And then you actually say, because at the end of the day you're doing a sense-amp comparison, are you to the left or to the right of a prescribed threshold? You have multiple thresholds. So let's say if you have 3 thresholds, if you read all 3 thresholds, you can say whether you were in one of the 4 regions which 3 thresholds can determine, yes. But placement of the thresholds is actually a question in its own right, because depending on where you place the thresholds, you're going to induce a different quantized channel. And so if you induce the wrong quantized channel, then you're building a code for the wrong channel. So there is an issue, there is ongoing work being done in careful placement of the threshold reads if you have a fixed number of reads. Yes?
Can you go back to that figure which had all the
curves?
simulation curves?
The last one or the one before?
Last one.
Okay, yes.
They are typically interested in extremely low frame error rates.